to discuss another form of time series models that we actually call moving average models. Okay, we call it MA models. Okay, so the moving average models of order Q. Okay, I'm actually going to show you now what is the difference between the moving average models and the autoregressive models. The autoregressive models actually relate the current value of the time series to the past values. But in the moving average model, we are actually going to relate the current values of the time series with the current shock and the previously existing shock. Okay, as you can see right here, you're actually going to see that the current values of the series is actually related to the current shock, okay, the immediate past shock, and the previously existing shock. So that is actually the difference between the moving average models and autoregressive models. I'm actually going to say that once again. For the autoregressive models, we are actually relating the current values of the series, okay, to the previous values, okay. But in the moving average model, we are actually relating the current values of the time of the series to, we're expressing that as a functions of the from the previously existing shock. Now take a look at what I have in the fictive model. Now we have the present values of the series. We are actually relating that to, if you take a look at what I have here, this is a previous shock, okay, the immediate past shock and previously existing shock. So like I said, this is a population model and this is a fictive model, and the assumptions still remain that the WT, the stochastic component, is independently and normally distributed, which means zero and variance sigma square W. Okay, so like I said, the fitted moving average models actually use past residuals. Okay, if you take a look at WT minus 1, WT minus 2, up to WT minus Q, those are past residuals. Okay, so we're using the past residuals to actually predict our future values of the time series, just like what I said. Okay, do you know that the examples of this is the consumer price index that we call CPI. Okay, so if economic condition actually cause larger than expected increase in CPI, okay, a large positive noise, okay, then we might expect the CPI of the following month to be above what we can ever imagine, above what we can expect. Okay, so that's an example of moving average. Okay, okay, so moving average in another context, actually, commonly we used to denote the focus based on average of past values of a time series, and I'm actually going to walk you through an example right now. If you take a look at what I have right here, uh, there's one moving average that you've done before. We only going to add for instance, if you want to do three moving average, like what I'm trying to show you right now, is a three moving average. But this is not what this is not the moving average model that we're referring to. But what I'm just trying to let you know, this is moving average in another context. Okay, if you listen to news about COVID cases, they're going to tell you 5 days average, 7 days average. That is what I mean. Okay, so that's what you can see right here. And then when you take a look at what you have here, what is it looking like? This is actually looking like an autoregressive model of order 3. Okay, if you basically remember what we did before on autoregressive model. So this is an autoregressive model of order 3. Okay, so what I'm trying to say, all right, now it is not the same as a moving average model. What you see here is not the same as moving average model, but this is basically um using moving average in another context. Okay, uh you know, which what I've specified right now is an auto regressive model of order 3. And you know what, so because the moving average model that we're dealing with right now does not actually have past observation y in the model. Okay, you know, if you take a look at what I have here, um this has a past observation y, you know, yt minus 1, yt minus 2, and yt minus 3. They are the past observation y. So, and that does not qualify them to be a moving average model, because what we expect in a moving average model is to have is how we can actually relate the current value of the series, or say as a function of the previous residuals. Okay, now you remember the other time under the autoregressive models, I walk you through autoregressive model for that one or that two and stuff like that. So in the moving average model, we also have moving average model for that one. We have moving average model for that two as well. So when you take a look at what I'm trying to show you right now, okay, so this is a population model for that, and of course this is actually we are the fitted model. Okay, so this is a fitted model. When you take a look at what I have right now, it's more or less as dealing with a simple linear regression where you have only one predictor in the model. So if you take a look at what I have here, the only predictor that we have in this model is actually this guy here. Okay, this is just a white noise. Okay, so you can see that the current values of the series is actually being related to the past residual, and of course the distribution of the random component has to be normal, which means 0, and variance sigma square w. Now, just like the same way that we have a property of autoregressive model for that one, you remember I show you the way to find the mean, to find the variance, and to find the autocorrelation, right? When you are dealing with the autoregressive model for that one, we also have a way to obtain the mean, the variance, and the autocorrelation when when you have the moving average model for that one. So take a look at what I have here. The expected values of yt, okay? The expected value of this is actually equal to, you know, the expected value of this is going to be 0, and this is going to be 0. Then the expected value of yt is just going to be equal to mu. Okay, I think you know that. Okay, so then the variance of yt is this. Okay, this is the formula. So if you're given the moving average model of order 1 and you want to figure out the variance, this is the formula you're going to use. Now when you take a look at this formula, you're going to see the sigma square w is just going to be the variance of the noise, and of course the a1 square is just going to take you know, the a1 here, okay, which is more or less the slope, which is more or less the contribution of the past residual, okay, on the response. And if you want to find the autocorrelation, okay, the autocorrelation at lag 1, okay, for MA1, the autocorrelation at lag 1, then you're actually going to make use of this formula right here. And let me tell you this, if you're dealing with the the moving average model, moving average model for that one, then any autocorrelation that is greater than lag k, k that's greater than 1, where the lag is greater than 1, the autocorrelation is actually going to be equal to 0. Okay, I just wanted to take note of that. Okay, so what I'm trying to talk about here is just that, okay, if the variance of yt equal to the variance of the noise multiplied by this quantity, then what that implies is that the variance of yt will be greater than the variance of the noise. So that is what I mean. Okay, so you know, Since the ACF plot shows the estimated autocorrelation at different lag, I think you know that, then the ACF plot for a time series generated from MA1 model cut off after lag 1. Now there's something I want you to take notes. Okay, the other time when I was discussing moving average model of order 1, okay, now if for something, for a time series model to be a moving average model, or I mean to be autoregressive model of order 1, okay, we expect the autocorrelation function at different lag to decrease to 0, and we expect a partial autocorrelation function to cut off after lag 1. Okay, I'm going to say that again. For autoregressive model of order 1 that we have done before, okay, uh, if you observe the autocorrelation function of that, we expect the autocorrelation values at different lag to decrease exponentially to 0, and we expect the partial autocorrelation function plot to actually cut off after lag 1. But when we are talking about the moving average model, okay, we are actually going to switch the uh, the autocorrelation function for partial autocorrelation function. Okay, now when you're talking about moving average model, as the ACF plot will actually show that you know a time series generated from MA1 model to cut off after lag 1. Remember, what normally cut off after lag 1 was a PACF. Okay, using a PACF for autoregressive model, okay, it will cut off after lag 1 for a arrow of order 1. But what is going to cut off at lag, what's going to cut off after lag 1 in the moving average model is actually ACF plots and not PACF plots. So, and in that case, the partial autocorrelation function then for MA of order 1 will decrease exponentially to 0. You know, I told you we're switching that. Okay, so we have, like I said, I want to walk you through an example right now. If you take a look at the model that we have right here, this is a moving average model of order 1, right? Okay, you were given the distribution of the noise, you know, you have the mean and the variance, and probably they ask you to derive the mean and variance. And how are you going to derive the mean and variance? And that is what I want to show you right now. Okay, deriving the mean and variance, you're going to find the expected value of YT, right? Take the expectation of both sides, right? The expected value of a constant is actually going to be a constant. And don't forget, under the assumption, the expected value of WT have to be equal to 0. Okay, the expected value of a noise, okay, whether the current values of a noise or the previous values of a noise have to be equal to 0. So because of that, this guy here is going to be 0, and this guy is going to be 0, and at the end of the day, the expected value of YT is going to be equal to 2. Okay, so that is how I got the expected values of YT to be equal to 2. So which means the mean of the YT, the mean of the model, is actually equal to 2. Now, if we derive the mean to be equal to 2, how can we actually derive the variance? Okay, now if you want to derive the variance, we can go by this form or simply use the formula that I show you here. Okay, you can actually use the formula here, or what you just need to identify what is the variance of the noise and what is the A1 in your model. Okay, you can just plug that in. But if you want to go through the rigorous derivation, then you can use the method that I used the other time, where you want to find the variance of YT, and of course the variance of all this one is the same thing as that, and you can actually split this to the variance of WT plus the variance of that. Okay, take a look at that, and minus 0.8, the constant is going to come out and it's going to be squared. Then what is the variance of WT? Of course, you've been given the variance of WT is 0.25. You're just going to plug in, you're just going to plug it in. Okay, that's what I just did, right? Okay, and plugging it in on, of course, that is what we got. So at the end of the day, you're going to see that this is similar to using the formula that I showed you before. Look at that. The sigma squared is 0.25, which is this guy, which is the variance of the noise, and 1 plus A1 squared. Now, don't forget that your A1 is actually minus 0.8. When you square minus 0.8, it's going to give you 0.64. So like I said, you can make use of this formula right here. Okay, now for autoregressive model of order one, the other time I walk you through deriving the mean, deriving the variance, and deriving the autocorrelation. Now for the moving average model of order one, okay, I think I've walked you through how to derive the mean. I've walked you through how to derive the variance, and what we want to do now is actually to walk you through how to derive the autocorrelation at lag one. Okay, so if you want to derive the formula, okay, like uh, this is the formula that we're going to use. Okay, this is a formula we just need to plug in year one in the model. But what I'm going to show you here is just how to derive this formula right here. So, but you know what? It's not that required that you should do that, but what you just need to know is the end formula that you can actually use. Okay, for instance, if you want to find the autocorrelation function at lag one, okay, you need to identify your A1 in the model. Your A1 is basically going to be minus 0.8. Okay, just going to plug that in. Okay, so this is a process of deriving the formula in case you care to know about it. Okay, so the model, the ME of order one is actually giving us this. You know that the correlation is just the ratio of the covariance of the current values of the series and the past values of the series divided by the square root of the variance of yt and the variance of yt minus 1. And of course, the yt is actually MA1, which is this guy here. And using this, I can also obtain the yt minus 1, right? I'm only subtracting 1 from the subscript t here to be able to arrive at this. Okay, now if you want to find the numerator right now, then it means you want to find the covariance of yt, the whole of this is yt, that's why you are plugging it there. And for yt minus 1, you're going to put the whole of that. Take a look at that. And you now want to find the covariance. Okay, now if you want to find the covariance, of course, mu is a constant. Mu is a constant. It's going to be out. You're only going to have just this guy here, which is this one here, and you're going to have this guy here, which is this guy here. Okay, now mathematically speaking, the covariance of that is just going to be A1 variance of WT minus 1. And of course, this is A1. The A1 is actually here. And what is the variance of WT minus 1 is actually sigma square W. I told you the other time, the variance of residual, whether the present values of residual or the previous values of residual, the variance is actually going to be sigma square W. Now, what about the denominator now? So you want to find for the variance of YT. Okay, I show you the formula the other time. The variance of YT is this guy, here. So the variance of YT and YT minus 2 or variance of YT minus 1 or whatever, okay, is still this guy here. Okay, so the variance of YT is this guy, the variance of YT is also that. So when you actually find, you're taking the square root of that, if you multiply, you're still going to have that. Okay, now what you're now going to do, the correlation is a ratio of the covariance, so that you're just going to use this guy here. You're going to use denominator here to divide this guy here. And of course, this is going to cancel that. Then I have this. And of course, that is the formula. Okay, if you want to do that at lag 2, of course, what are you actually expecting? If I'm talking about MA of order 1, and I want to figure out the autocorrelation at lag 2, of course, what you're actually expecting, that it should be 0. Okay, I told you before, that if you're focusing on any of that one, of course, the only thing you can actually find is the autocorrelation at lag one. Okay, so any lag greater than one, the autocorrelation is actually going to be equal to zero. So which means for um MER for that one, the only autocorrelation value we can obtain is at lag one, and any lag greater than one is actually going to be zero, and that is the reason why at lag two here you can see we're able to show that is equal to zero. If you follow what I did right here, then you're actually going to get zero out. Okay, so how are you going to get zero out? This is YT, right? Take a look at that. That's YT. And for YT minus 2, it means I'm actually going to subtract 2 from here, 2 from here, 2 from here. It's actually going to give me all this one. And if I want to find the numerator out now, I want to find the covariance of that. So all what I'm going to put is for YT, I'm going to plug in the whole of this. Take a look at that. For YT minus 2, I'm going to plug in the whole of that. Take a look at that. And the covariance of that, the constant here is mu, right? The mu. Okay, so the covariance of that, you're going to remove the constant out. So I'm actually going to have this. Okay, and you know what, if you take a look at all what I got, this is like a noise WT, the current values of the noise, the immediate pass of the noise, pass of the noise, and the previously existing values of the noise. Okay, then I want to tell you mathematically the covariance of that is actually going to be equal to zero. And when the numerator of a fraction is zero, then the whole thing is going to be zero. And that is the reason why we said the autocorrelation for MA1 model at a lag 2 is going to be zero, not only at lag 2, at any lag greater than 1 will be zero. Okay, so let's now generalize right now the MA of order Q. Okay, the MA of order Q is that, and where the WT is a distributed normal, and of course the property is that the mean of YT is going to be mu. Okay, for any MA of order Q, whether order 1, order 2, order whatever, the expected value of YT is actually going to be equal to mu. And of course, the variance of YT, if you look at what we did when we're dealing with MA of order 1, in MA of order 1, we actually said the variance is actually going to be, sigma W squared into 1 plus A1 squared. It's because I'm talking about MA of order 1. If I'm talking about MA of order 2, where I got like two slopes, of course, I'm going to have 1 plus A1 squared plus A2 squared. Now, I'm going to show you something now. We're talking about moving average of order Q. Of course, you're going to have an extended, look at that. So the variance of YT, we're going to be sigma square W, then you're going to have 1 plus A1 squared plus A2 squared up to AQ squared, because I'm talking about ME of order Q. Take a look at that. Okay, so, and which also implies that the variance of YT is automatically just going to be greater than the variance of a noise. Okay, and the reason why it's going to be greater is because of the entity right here. Okay, take a look at that. Okay, and you know what? The autocorrelation functions, will be equal to 0 after lag Q. Okay, we actually be equal to 0 after lag Q, just like what I said. And you know what? The MA models are always stationary. Okay, the MA models are always stationary. Okay, we assume that the MA models are always stationary. Okay, now the next thing that I want to talk about is how do we identify, and they have, you remember, I actually walk you through within the different orders of autoregressive model. Of course, we have a way to identify which of the AR model order is appropriate for a time series data. We're also going to do the same thing for MA models, but you know what? I want to have a recap on how we identify an ARO of other P models. Of course, to identify an ARO of other P models, when you plot an ACF plot and you realize that the estimated autocorrelation actually decay as lag increases, of course, that implies an AR model. And of course, if you want to know the appropriate AR model, whether it's going to be AR model of order one or it's going to be AR model of order two, then you needed to plot a PACF, right? The PACF, when you see that the autocorrelation function cut off after a particular lag P, then of course the appropriate model is going to be AR of order P. So what I'm trying to say is that specifically is that if the partial autocorrelation cut off after lag 2, then it means the appropriate model is ARO for that too. And of course, as you can see in the plot, this is an ACF plot. You can see it's actually decreasing at different when the lag increases, and that is actually indicating an AR model. Okay, and of course, when you look at the partial ACF, then you're actually going to see that after lag 1, okay, you're going to see that after lag 1, it's actually cut off. So which means the ARO of other one is actually appropriate. Okay, and that was why I said the PACF value. And for the PACF, I told you the other time, the PACF we actually start, we not include lag 0. I told you it is the ACF that we always include lag 0. Okay, but the PACF we always start at lag 1. Okay, I just wanted to take note of that. And what the two plot above, what they are actually suggesting is that the arrow for that one is actually going to be appropriate. Okay, you know, we can see the ACF plot here, we're going to give us the knowledge that, okay, because the autocorrelation function decay to, decay as, as the lag increases, it's actually going to confirm that, okay, AR model is appropriate. And if I want to know what particular order of the AR that is appropriate, then I'm actually going to go for partial ACF. And what you can see right here, after lag 1, immediately after lag 1, all this actually cut off. So which indicate that ARO of order 1 is actually appropriate for the model. Okay, now that we've done that, how can we also identify MA of other Q models? Okay, if you want to identify the MA of other Q model, I told you the other time we're going to switch it. Okay, situation where a PACF plot, the estimated partial autocorrelation decay as lag increases, then the appropriate model is actually going to be an MA of other Q. Okay, and when the ACF plot told us the estimated autocorrelation cutoff after lag Q, then it's going to tell us MA of other Q. So if you take a look at the way we identify here, MA model is different from the way we identify autoregressive model. So this is the ACF plot. And as you can see, the ACF plot cut off after a particular lag. Okay, and why the PACF plot decay to 0. So this is a reverse of what we did in autoregressive model. Okay, and what this actually implies is that MA of order 1 is appropriate for this time series. Okay, so look at that. It is the ACF plot here that will cut off for MA. Okay, so not the PACF as we have in the autoregressive model. Okay, now I walk you through simulation study in autoregressive model. We can also simulate data set for moving average model. Now we here we want to simulate 2000 data set. Okay, for this population model, this is moving average model of order 1. Okay, and of course the distribution of WT or the noise is identically and independently distributed with mean 0 and variance 1. Okay, so this is the code in R. Okay, I told you the other time the essence of setting a seed is for reproducibility. Okay, so you're gonna write y equal to arima dot same, and of course the numbers of data set, the model. Of course, what is missing right here, okay, is actually 0. You know, 0.8. Okay, and of course, what is missing here is gonna be 6. It's gonna be the mean. Okay, you're gonna put the mean right here. Okay, that's what is missing. So the moment you are done simulating your data, just like what we did before, you can actually find the sample mean by writing this code and the variance, and that will give you opportunity to compare the sample mean, okay, with the population mean. You know, the population mean here is 6. The sample mean is 5.97. They are very, very close. And of course, the population variance, you know, if you use the formula that I showed you before, the formula that has to do with sigma squared multiplied by 1 plus a1 squared, of course, you will use that to determine the population variance of the model, and you can now compare that with this to see if they are close. Okay, so as you can see, um, you know, like I said, the theoretical mean is actually 6. The sample mean is that, okay? And of course, the theoretical variance is 1.64. And some of you may be wondering, how do I get 1.64? For you're going to use the variance for MA or for that one. I'm going to show you now. Okay, so the variance of MA of order 1, yeah, you're going to make use of this formula right here. Okay, you're going to make use of this formula right here. Okay, that is the theoretical variance. This is theoretical mean. Okay, take a look at that. So, but you are comparing the theoretical mean with a sample mean and the sample variance, and to see whether they are close or not. So that's exactly what we're trying to do. So the population mean is 6, the sample mean is 5.974751, and the theoretical variance is 1.64. The sample mean is that. Okay, so identify appropriate time series model based on the Acf plot and the PACF plots. Okay, so you have one of in a situation where you are actually giving Acf plots this way and the PACF plots, and they actually ask you to identify a time series model. So based on what we've done before, you can actually you know, answer that. Okay, so we actually generated this plot using the data set, you know, the 2000 that we generated before using this population model. And of course, for learning purpose, I will fit a model to time series data if though I already know the population model. Okay, now this is the coding now. Okay, now you remember the other time when I was dealing with ARO for that one. Okay, we normally write 100, but for MA or for that one, it's going to be 001. So take note of that. So based on the simulated data, we fitted the model. Look at what we got. Okay, you remember we did the same under the autoregressive model. You know, after estimating the parameter of the fitted model, we compare with the true parameter in the model. Okay, so the estimate of the parameter here, this is the intercept, and this is the one that is acting as a slope. Okay, now if you plug it in into the MA of order one model, okay, intercept in the MA of order one model is always the mean. Look at that, plug it in there. Then your A1 is this guy here, okay, to 2 decimal. That's what I have. Okay, so this is a MA of order one. This is a fitted model. So if this is a fitted model, okay, we can actually have a way to make a prediction, okay, and that is what we want to do now. Uh, you know, the data set that we are actually using ended up in year 2000. In 2000, don't forget we simulated 2000 data set. Okay, we simulated 2000 data set, and you know what, I may want to have a prediction like predicting three values ahead. So which means I actually want to make a prediction for 2001, 2002, and 2003. And of course, this is going to be the code now. So since I'm predicting three values ahead, I'm actually going to write predict mode and dot ahead equal to 3. Okay, and automatically you're going to be given these three results. So 5.276312 now is a prediction for 2001, and this is for prediction for 2002, and this is a prediction for 2003. Okay, this is how we make prediction using the MA of other one model using the hard code. Okay, so the next thing that I actually want to talk about now is if you want to use your model, okay, to make this prediction, like what I'm trying to show you here is when you make use of R code, you get this result. But if you actually want to use a fitted model, okay, you want to compute that manually, you want to make the prediction manually, okay, so all what you actually going to do, okay, you want to make use of the model right here. Take a look at that. This is a fitted model that you obtained the other time. Okay, if you want to make a prediction for 2000 for 2001, so you're going to plug in t equal to 2001, and if this is equal to 2001, this is going to be 2001 minus 1, which should be 200. Take a look at that. So which means if I want to make any prediction right here on what the value is going to be in 2001 data set or data point, then I need to know 200 residual. Okay, if I want to get it 200 or 200 residual, then this is going to be the code. I'm going to do mode $ residual. I'm going to put 2000, and that is going to give me that. And you know what, I'm going to plug in this guy here. Then at the end of the day, I will be able to, when I multiply this guy by 0.80 and add to 5.97, then I will be able to have a prediction for 2001. Okay, and if I want to do the prediction for 2002, when I plug in t equal to 2002 here, this is going to be 2002 minus 1, which should be 2001. Okay, and I'm actually going to do just like what I do here the other time to get that of 2000. I'm also going to do that for this. So then I'm also going to do that for that. Then with that, I'm actually going to get my results. Okay. Um, how do we now identify the appropriate time series model based on the Acf plot and the PACF plot? Okay, take a look at this. This is the Acf plot. Okay, and for MA models, okay, the ACF plot, if you want to know the appropriate MA model, then you need to look at when does it cut off. Okay, after what lag does it cut off? You can see here after lag 1 2 it cut off. Okay, and then here this actually the PACF for MA decay exponentially to 0. And if somebody tell you what kind of model is that, I'm afraid it's going to be MA of order 2. Okay, so that's going to be MA of order 2 because it's cut off the ACF cut off after lag 2. Okay, lag 1 1 2. So after that it's cut off. And don't forget, I told you when you are talking about MA models, okay, it is the ACF that cut off after a lag. But when you talk about autoregressive model, I mean AR model, then we talk about PACF that cut off. Okay, so this is the model I use to generate the time series data. Take a look at that. Okay, and you know what? If you based on what I have now, so this is the model. Okay, you can see it's moving average model for that too. Okay, so and if you want to know, you know that if you want to simulate 2000 data sets based on this model, or what you just need to do, you're gonna, what is the MA parameter? Okay, you're gonna indicate 0.8 and it's 0 and minus is 0.2 right here, right? And of course, what you're gonna have right here is actually gonna be 12. That is the mean. Okay, here is gonna be 12, and here you just put the MA parameter. You put 0.8 and minus 0.2. Okay, and if you copy that into R, automatically you're actually going to uh, have your data generated, and of course based on that data set you can actually obtain the time plots. You can do ACF plot, and you can actually get the PACF plot. Okay, so what I'm trying to show you right now is just the code in how to figure that out. Okay, some values are mixing here, and of course you know how to actually fill it up, right? So what you're going to put here is actually going to be the parameter of moving average model for that too. So zero 0.8 is going to be here, then minus 0.2 is going to be here, and of course right here is actually going to be the mean, which is going to be 12. And when you have that in place, then you have your data set generated. Okay, so this is going to be the end of the part one, the first slide. As I'm actually going to share my second slide right now. In case you need clarification, you can actually reach out to me during my office hours. Okay, so I'm going to put up my the other slide right now. Give me 1 second. Okay, this is going to be the last slide of the semester. Okay, and I call it time series analysis, part 7. So actually call it case study. Okay, before now, you've been introduced to time series analysis, and we've learned about a lot of a plot like time series plots, the ACF plots, PACF plots, and so on, like that. Okay, and of course, you've learned about different kind of time series models. I think I've walked you through what we call the autoregressive models of different orders. We've also done the moving average models. Okay, now let's now talk about the case study right now. Okay, if you take a look at what I'm trying to show you right now, we want to actually use time series model, okay, to model the study of Arctic sea ice. Okay, if you take a look at what I'm trying to show you now, okay, the sea ice extends actually the area of sea that has more than 50% ice. Okay, the satellite images help scientists to record the sea ice extent. So as you can actually see right here, okay, you can see I have Russia, Alaska, Canada, the Greenland, and Europe. Okay, take a look at that. Okay, so the sea ice extents actually fluctuates seasonally, reaching the largest amount in February or March and shrinking to the least amount in September. And this behavioral pattern has actually been observed by time series modelers. Okay, so we will use the September sea ice extent data, which actually start from 1979 to 2008 for analysis. Okay, now if you want to have access to the citation is actually from FETRA and ETOR. Okay, 2007 17, which was updated daily. Okay, you can actually check the Boulder, Colorado, United States, the National Snow and Ice Data Center. Okay, okay. We have some data set right here from 1979. Okay, just like what I said, from 1979 to 2018, but I'm only just showing on 4 observations right here. Okay, we have the months, we have the data type, we have the region, we have the extent, and we have the area. Okay, and of course, if you want to have access to the data, you want to read that into how you actually the name of the data is actually saved with Arctic Seal Ice.csv. Okay, and the moment you press that, you actually have the access to the data. Okay, now when you have a time series plot of the data, okay, let's see what we're going to have. Now, this is a time series plot of the data set, okay, from 1979 to 2018. You can see kind of decreasing, right? Take a look at that. Okay, so the question now is, when can I fit a time series model to this data? Excuse me. Let me tell you this. When you have data set, okay, the very first the preliminary investigation is constructing a time plot. When you take a look at what I have here, this is the preliminary investigation. We are actually uh, having the plots of the series over time. Okay, when you have that, then the next thing that you actually, why are you having the plot of the series? Because you actually want to see whether the stationarity actually hold. You don't expect the mean to vary over time, and you don't expect the variance to vary over time. And when you see a data set like this and you see a time plot like this, and the question now is, can I actually fit a time series model to this data? Okay, so if you want to fit a time series model to this data set, um, because the major assumption in time series is actually stationarity, then I need to check the stationarity. Okay, and of course, checking the stationarity, okay, we will like the nature of the relationship to stay stable over time, because staying stable over time means there is no upward increase or downward increase. Of course, we want stability. Okay, so if that occur, then we're going to say that a time series is stationary. Otherwise, we couldn't use a model built from early values to forecast relationship later. Okay, so as you can actually see in the time plot, the time plot actually giving us the notion that the mean is not constant over time. And of course, based on what we've done before, what you're actually going to do, if the mean is not constant over time, it means there's actually going to be violation of seasonality. And what needed to be done is to difference, right? Until you remember that we difference, okay, you're going to difference at lag one, okay, and if that doesn't work, then you can actually difference further. But right now, after differencing at lag one, okay, this is the coding now, then I'm actually going to replot again. And when I replot again, what did I see? Oh my God, take a look at what I'm seeing right now. This is actually the mean of the series is looking as if it's constant over time. Okay, so and that was why I said taking the difference at like one actually help us to remove the obvious violation of stationarity. Okay, so the very next thing you're going to do is to actually plot the ACF plot of the difference. Okay, so plotting the ACF plot of the difference, you can actually see uh, what I have right now. Okay, you can see what I have right now. And the partial ACF, this is what I have. Take a look at that. And of course, what does that implies? Now, you're actually going to see that you remember in last class I told you there's possibility that you know the plot that we're using in time series could suggest more than one potential model. Okay, when you take a look at what I have here, okay, if you want to use the notion of ACF, this actually cut off after lag one. Okay, this may be suggesting an MA of other one. Okay, it may be suggesting an MA other one, and of course so based on what C, and of course also maybe suggesting an ARO for that one. Okay, and also it may be suggesting an AR of other three as well. Okay, so because of that, we are actually so based on what we see. And if you look at the partial ACF on the other hand, then you're going to see the partial ACF is actually suggesting that okay, probably it's going to be ARO for that one, because after lag one here, you actually see that it's cut off, right? and this is, the PACF is actually suggesting the ARO for that one, and it's also suggesting ARO for that three. If you take a look at this, after lag three, it cut off again. So the PACF here is actually suggesting ARO for that one and ARO for that three, and the ACF here is suggesting MAO for that one. I think I'm going to say that again, for you to really understand. If you look at the ACF plot, because it's cut off after lag one, take a look at that. It's cut off after lag one. Of course, it's actually suggesting MAO for that one. But when you take a look at the PACF, okay, it's after lag one here, it's cut off, okay, and after lag three, it cut off. So the PACF here is actually suggesting autoregressive model for that one and that three, and now there's a conflict. There's a conflict now because the two models, the two plots is actually, suggesting three models. Okay, we got MAO for that one, we got MAO of ARO for that one, we got ARO for that three, and now the question now is, how are we going to arrive at the best model? Okay, we got three competing models now. Okay, now this is what you're going to do. We're going to fit each of the model using the R code. We're going to start by fitting ML for that one. Okay, I told you. And don't forget the data we're using is the one we have already defined. Okay, and the code is going to be 001 for ML for that one. This is the result that we have. And of course, we have, some criteria that can be used. Okay, situation where you have more than one computing model in time series. Of course, this is the time that we actually going to be using the criteria of a sigma square estimated, the log likelihood, and the AIC. Now, based on the model here, based on the coefficient estimated, of course, we're going to have you can write your fitted model. Now, let's go into the ARO for that one. I fixed that as well. Okay, it's going to be 100. This is what we have. I can also actually ask you to write a fitted model. Okay, so this is what we have. Then we're going to fit ARO for that three. Oh my God, that's what we have. Okay, for the ARO for that three, this is what we have. It's just going to be ARIMA 300. Take a look at that. Okay, now we've fitted all of that. Then what we can do you know that we can actually conduct what I call diagnostic testing? Okay, what do I mean by that? We can evaluate our model by trying to actually investigate the behavior of residual. We want to see whether the residual is going to behave like a white noise. Okay, now let's all first get the ACF of the residual for MA or for that one. What do we expect the behavior of the ACF or residual to be? We expect virtually all the autocorrelation value to be within the blue dotted line. Until you remember that, for them to be within the blue dotted line means they are actually zero. Okay, it is only when that happens that we can actually say that the residual actually behave like a white noise. Now, for the MA of order one, you can see what I have. The only bar that is out here is the autoregress or is the autocorrelation value of function at like zero, which is expected. And what this implies is that MA1 is actually adequate because there's no violation. Okay. Now, if you take a look at a arrow of order one, okay, the ACF of the residual for ARO for that one, we also have that one, and for that of the ARO for that three, we also have that one, and you can see the question now given each of these. So do the residual behave like a white noise? But I'm going to tell you, because most of the autocorrelation values are different lag, they are all within the blue dotted line in each of the model, then I'm going to say the residual behave like a white noise. Okay, so which means all the three suspected model actually pass a diagnostic testing. Now, okay, if they are all passed, then how are we now going to identify the best model? How are we going to identify the best model? Because they've really passed the test, they've passed diagnostic testing right now. But I told you the other time what we're actually going to use eventually is to use the model selection criterion. Okay, situation where time series models are competing. Of course, you've carried out a diagnostic testing, all look good, the residual behave like a white noise. Then all what you're going to do now is to use other model selection criteria to do the job. Okay, and of course, when you were estimating each of the model the other time, we have the sigma squared estimated, the log likelihood, and the AIC. Of course, I'm actually going to make use of the AIC. Now, take a look at the computing models right now. We've written out the estimated variance. We've written out the AIC. And of course, the one with the lowest AIC will actually be considered as the best model at the end of the day. As you can see, the MA of other one has the lowest AIC, and because of that, because of the fact that it has the lowest AIC, then we're actually going to choose the MA of other one to be the best among the competing models. Okay, so since we've chosen MA of other one, then it means if we want to make any prediction about the Arctic ice extent of 2019. Don't forget our data point actually we ended in 2018. Don't forget that it is between 1970 I think 79. Okay, I'm right. 1979 to 2018. And we can actually predict for 2019. Okay, we find ourselves in a world where we are so anxious about what is going to happen in the future. Okay, because why are we so anxious about what is going to happen in the future? Because we live in a stochastic world. Okay, so we're going to use the best model right now, which is MA of other one, as as a judge by the values of AIC, because it has the lowest AIC, then I'm actually going to use the MA of other one to make the prediction. Okay, now because I want to make a one ahead prediction, okay, for 2019, then I'm gonna write that predict MA1. Okay, that equal to 1. Then you can see what I'm having right now. Okay, so what is going to come out from the prediction is going to be delta Y40. Okay, delta Y40 is actually going to come out from the prediction. You know why we have a delta? Because don't forget the data set that you are actually using is difference. Okay, the data set you are using is actually difference, and that is the reason why your prediction you're actually going to write data Y40. Now, why am I writing Y40? I'm going to tell you why I'm writing Y40 now. Give me 1 second. You're going to see. Okay, you know that we actually our last observation, I think we have 40 observation, okay? We have 40 observation, and we want to make a prediction for Y41 because the Y41 we actually correspond to 2019. I think you know that, but you know what? What will come out of the difference from the prediction? Okay, what will actually come out is actually going to be you're going to call that data Y40. Okay, it's going to be data Y40. Okay, now, and data Y40 is actually Y40, prediction value for Y41 minus Y40. Okay, and this guy is this guy here, and this is what you actually want to find. And of course, this is the last point in your data. Okay, this is the last point. The Y40 actually correspond to the data point for 2018. I'm going to say that again. The Y40, okay, correspond to the data point for 2018. And of course, the data Y40 is actually the one that you predicted right here. And of course, this is what you're actually looking for. So all what you're just going to do now is to follow false. What is your Y40? You're going to write your data 40. You're going to have that. Then you're going to put this guy here and you're going to put this guy here. And of course, you can find this. The finally, your prediction is going to be 4.45. Okay, that is going to be your prediction at the end of the day. Okay, if you want to use ARO for that 3 to make prediction. On the other hand, even though based on the AIC, we actually use MA1, right, to make prediction. But if you also want to use the ARO for the three to make a prediction, don't forget, because you are using a difference data set, you actually this is going to be your model. 0.07 is the mu, okay, and this guy here and this guy here and this guy here, they are actually the parameter in the ARO for the three model. Okay, I think you know that. Okay, so we want to predict the same thing that we predicted using MEO for that one. The very first thing we need to do is to first predict data Y40 that I talk about. Okay, and or what you're gonna write, okay, you're gonna put 40 right here. Okay, 40 minus 1, that's gonna be 39. 40 minus 2, that's gonna be 38. And 40 minus 3, that's gonna be that. Okay, look at what I have now. Okay, now I want to tell you that we actually want to get this guy for 39, for 38, or for 37. Okay, and for the difference data set, and that is the values that you're actually going to have, because we need to plug them in. Okay, so take a look at that. That is for data y37. Okay, and that is for data y38, and this is for data y39. Take a look at that. So I actually needed to plug in all this into this model, so that I will be able to get data y40. Okay, I will need to get data y40, and you know what, when I get data y40, I still need the prediction for 41, because before I can actually get the predictor for 41, I need to first use this model to get data y40. Okay, so when I plug in all this one here now, I'm actually gonna get the data y40. Okay, the data y40 is minus 0.22. Okay, as you can see there now. Okay, and don't forget the relationship that I talked about the other time. If I want to get y cap 41, I'm actually going to add the y40, the actual y40 to data y40. And you know what? I've already determined my data y40 using the fitted model to be this guy here. Or what I'm going to do, I'm going to plug that in. And what is my y40? Of course, the y40 will actually come from the last point in the data set. Or if you better say, if you want to find that, you can just write your data and indicate 40 is going to come out. And then again, we got 4.49. Okay, using the MA model of other one, what was the prediction? The prediction was the predicted value for 2019 for active eyes was 4.45, and using the ARO of other three, it is actually 4.49. So are they close? Okay, kind of. They close, kind of. Oh my God, that is gonna be the end of my lecture today, and that is gonna be the end of my lecture for this semester. Of course, I'm actually gonna meet you on Monday to have review on the final exam, the final questions on how the final exam will be conducted. If there's anyone of you who actually want to ask question or who need clarification, you can meet with me during my office hours. Of course, I'm going to conduct my office hour on Monday. I'm also going to conduct my office hour on Tuesday. And of course, in each day, my office hour is actually going to start from 10 a.m. Okay, don't forget your exam is going to be conducted between July 28th and July 29th. Okay, and that is the reason why I'm going to have my office hour on Monday, and I'm also going to have a review on Monday. So I want to appreciate everyone that will watch this video. Make sure you guys stay safe and have a good day. Bye for now, guys.